regression. There are going to be a fair amount of notes first, and then we'll start looking at the homework questions after that. So let's start by what is a scatter diagram. Here are two examples of it. Imagine that you collected data on a number of cars, and you had brand new car, 1 year old, 2 year old, say 3 year old, you plotted it. And here's the value of the car. So, maybe 30,000, 20,000, 10,000, and so on. So basically, all you're doing is plotting the age of a car against what the value, say the Blue Book value of that car would be. And what you'll notice here is that there is a trend in this data. It's not that it's a perfect straight line, because that's not what happens in real life. But would you agree that there is a definitely linear, that just means straight line trend through this data? If I was doing a guesstimate, I'm not very good at drawing straight lines, so I'll fix that by adding in some more data points there. Can you imagine that might be what the straight line looks like? And when you draw a straight line through a scatter plot, we very often call that linear, which means straight line. And the other word that we use is regression. So that's basically the best fitting straight line through some data points. So I'm going to introduce you to quite a lot of the jargon today. The guy that's the age of the car in this case, oops, and this guy over here. This first fella is, oh, got somebody coming in. Chris, can you remember what I called that fella?
Sorry,
Yep.
middle for the mute
So
button.
this fella. What were you saying there?
Oh, sorry, I had to fish for the mute button.
Oh. So do you remember what we called the x-axis variable? The y-axis is called the response variable. What was the x-axis one called? It has a number of names.
Does it start with an E?
It does. That's close enough. Explanatory.
Yeah. All right. I knew it was an E word.
Yep. So explanatory variable, response variable. There's a homework question that asks you about that. So what we're saying is that the age of a car explains its value. If you think about that, that kind of makes sense. Would you agree that a brand new car, same make and model, a brand new car should cost the same, there should be the same connection that a brand new car is quite expensive, and the same car 4 years older shouldn't be as expensive, right? The age of a car has a direct reflection
once you drive
on
it off
the value.
Once you drive it off the lot, like 30% is gone right there.
Yeah, so you can imagine an immediate drop in the price. Now, in this set of data here, we're plotting the age of a child. So you imagine a 1 year old, a 2 year old, a 3 year old, 4, maybe up to 5 year old. And going up here is the height of that child. So you collect data on lots of children. So that's a 1 year old, and that 1 year old is, 20 inches and 40, 60, whatever it is. And you've got the height and the age. So in this case, the age is the explanatory variable, and the height is the response variable. And some lines, something like that, might represent the best fitting single straight line that you could do through that data. Now, when we do scatter plots, we introduce some terminology that we use to try and describe some of its features. So I'm not going to put any labels on these for speed, but imagine we had a scatter plot that looks something like this. Right? Well, when the data is going down the way, right, like this. Oh, and let's put the opposite version. Sometimes you get data, right, where as X gets bigger, Y gets bigger, like something like that. Imagine the best fitting line might look something like this. We say this fella has negative correlation. And we say this fella has positive correlation. So lines that go up the way are positive, lines that go down the way are negative. The easy way for me to remember is, doesn't that have a positive slope and doesn't this have a negative slope? Positive and negative correlation. So in this case, as the X gets bigger, the Y gets smaller. So that might be age of car, for instance, that one there. Can you see that's negative correlation? And here it is positive, right? As you get older, you tend to get taller up to a point. Now, the next thing that we deal with is the strength. So here is 4 different types of correlation, right? Straight line data, right? So think correlation, linear correlation is straight line data. Now, in this one, we would say it was strong. Here we would say it's moderate. Here we would say it was weak. And here we would say there was none. Strong is when the data is very close to being a single straight line, right? All the data is really tight. Moderate is not quite as good, right? A little bit more spread out. Weak is even worse, right? And none, basically there is, that looks far too circular, right? Right, where there's no obvious pattern, isn't I just look at a random set of data. So one of the ways I look at this is I use the sausage test. So you can imagine a sausage being drawn around each of these situations, with the exception of the last one. If your sausage is really skinny, you've got a strong correlation. If it is a bit fatter than that, it's moderate. If it's very fat, it is weak. And if you can't even see a straight line, we say it's got no correlation at all. Are we good with that? Now, since I don't have to do too many diagrams, there is a special variable in statistics. It's called the correlation coefficient. And it uses the letter I. And the correlation coefficient is a number between 1 and -1.
What is the coefficient? Wait. Oh, sorry.
Say again.
What is a coefficient?
Coefficient is, in math, what is a coefficient? It's a correlation coefficient R. It's the full title for this thing, right? A coefficient in math typically just means a number. So it's a correlation number called R. And this correlation number, this correlation coefficient R, allows us, we can calculate it from the data, and it allows us to tell us how good the data is to being a straight line. So this one here is probably about 0.9. This one here is probably about 0.7. And this one here is probably about 0.5. And this one here is almost none. It might not be 0.0, it might be 0.1, but it's dead close to being nothing. So if you have some data and the correlation coefficient was 1, it means you have a perfect straight line going up the way. So that's what a correlation of 1 would look like. Can you imagine what a correlation of -1 would be?
Would it be a straight line just going the opposite direction?
Yes. It would be a straight line going down the way. So if I don't show you a picture, but I tell you that the data has a correlation coefficient R of 0.8, do you get a feeling that it's somewhere between these two? It's kind of, maybe it's strong, maybe it's moderate, but you can actually get away with that because what you can say is it's strong to moderate, right? You can kind of cover your bases. If you're not 100% sure, is it's close enough to be called strong, you can say it's strong to moderate. But if it was equal to 1, I'd be able to say, although I can't see the picture, it's a perfect straight line going up the way. And if it was -1, it's a perfect straight line going down the way. So far, so good. Any questions? So we've talked about scatter plots. You can say positive or negative. We can talk about strong, moderate, weak, or none. We've also told you that there's a number, a correlation coefficient R, that actually puts a number on how good the data is to being a straight line. And I've given you kind of signposts that you can use to kind of pseudo guess that. Now, imagine that you had a scatter plot, and we'll just have pretty boring data. And it looks something like that. Okay. Positive or negative? Positive correlation. Agreed. How do you tell? Did you agree it's sloping uphill? Right. You can't really judge numbers because it's hard to say, oh, that's a 0.6. And I wouldn't even expect anybody to be able to do that. But what's your best bet? Strong, moderate, weak, or none? What do you think this guy is?
Moderate.
I would agree. Can you imagine the sausage isn't very skinny, but it's not that fat, right? It's kind of middle of the road. There we go. Now, suppose there was an extra data point there. Just one guy sitting out on his lonesome. We have a name for any data point that is separate from the main body. Do you see my sausage has all the data in it, right? But that poor little guy doesn't belong inside the sausage. We have a special name for that. And it's a name you've actually heard before. What do you think you call guys like that?
Outlier.
Yeah. And that's an example of an outlier. Now, can you imagine that was a dot up there? Now you might say, wait a minute, the data's pointing like the sausage and that dot's in the same direction as the sausage, which it's meant to be, right? But would you also agree there's a big gap of nothingness? That also counts as an outlier. So an outlier can be anywhere. It can be in the same direction of the sausage. It can be outside the sausage. It can be above the sausage. It can be, I guess, down here if there was a scale enough for it. It just needs to be a data point that is not part of the main data. And I think it's easy to tell what numbers belong in the sausage and what numbers don't. Oh, and by the way, the term sausage is not a term that you're going to see in a textbook. It's just my way of expressing a visual idea, right? So, but I think it's quite a cool idea. Do you agree the idea of a sausage gives you a feeling for how you can, you know, how to look at a scatter plot? So, are we cool with that piece of information? So far, so good. So, Let's look at, well, I'll do it on a new piece of paper. Let's look at a scatter plot. And along the bottom, we're going to do age again. So it's the age of a child. And the vertical one here is just going to be the weight of that child. And so when they're very young, they don't weigh much. And then as the children get older, so each one of these dots is a different child, different age, different child. And I don't think it would be too unreasonable to expect that the data might look like that. Maybe you've got a slightly fat child, maybe you've got a slightly skinny child as well, but most of the data, would you agree, it would probably go uphill? Agreed? Now, if I tell you that the R value for this happens to be 0.8, and this is the x-axis and this is the y-axis, then I can say with a pretty degree of certainty, as x gets bigger, so in this case, as the age of the child gets larger, then y gets larger. Now, I don't need that picture to make that conclusion, because isn't a positive R value mean it's sloping up the way? So this tells me as the age of the child gets bigger, then the child's weight gets larger, right? Now, suppose I don't draw the scatter diagram, but I tell you its correlation coefficient is the number -0.7. As x gets, I think I'll use the word larger, as x gets larger, then y gets, insert missing word here. As x gets larger, what will happen to the y value if the correlation coefficient is a negative number like -0.7? Will it get larger or will it get smaller?
Smaller.
Right. And the reason for that is if it's a negative R, doesn't that mean it points downhill? Remember, positive R's point uphill, negative R's point downhill. And so it gets smaller. And if you did a scatter plot of it, it would probably look something like that. So can you imagine, as this gets bigger, the Y's get smaller. Are we okay with that? Does that make sense that you only need to know the R value to answer this question? What happens as x gets bigger? Because if it's a positive R value, as x gets bigger, doesn't the Y value get even taller? In this case, as x gets bigger numbers, doesn't the Y value get smaller? The next thing we're going to talk about is a very important saying in linear regression. And its correlation does not mean causation. What do I mean by that? You will collect data and it will be very good linear data, and the x-axis and the y-axis will be whatever it is, and you will say the reason this what this is telling me is that if the age gets bigger, the height gets bigger, or the first thing, the X's, is causing the second thing, the Y's. Now, in many cases, that is in fact true. I don't think it's unreasonable to assume that as the age of a child gets older, won't their height or their weight, whatever it is, get more? That would certainly be correct. So correlation is just, we're talking about this whole picture and the dots in it and everything else associated with it. So if you've got a nice linear scatter plot, it does not mean causation. It doesn't mean it causes it. And let's show you why that is the case. I'm going to give you two pretty standard examples of a scatter diagram that shows this relationship, or why it's true to say it. On the bottom, I'm going to have the average number of televisions per household. And up here, we're going to have the life expectancy. Right, now the life expectancy, probably should have done the two columns, is how old, on average, a person in that country lives. So each one of these dots I'm about to do is going to represent a particular country. So you have, on average, 1 TV in a household, 2 TVs, 3 TVs, maybe even some countries might have as many as 4 per household. And the data looks like this. It is very linear. And it has a good R value. And you can even imagine what the best fitting straight line might look like. It has all the features that a good set of data should have, right? Nice and compact, nice and linear. But you cannot make the assumption that this is causing that. What you're saying is the number of TVs in your household is the reason people live that age. I mean, if that was true, wouldn't America and all the rich countries in the world, instead of sending money and food and medicine and, you know, whatever else they choose to send to these countries to try and improve, you know, the life expectancy of these people? If this was true, wouldn't the only thing we do send them TVs? Just send them, you know, a couple of million televisions. That'll increase their life expectancy. What's happening here has a name. It's called a lurking variable. Why should the number of TVs that people in a country own make them live longer? What, in fact, is happening here? What is the real reason behind this pattern?
More wealthy countries probably have more TVs, therefore higher life expectancy.
That's the most common one, and that's the one I would have used. Now, when you are a wealthy country, America, Britain, right, most of Europe, if you're a wealthy country, you do tend to buy more TVs and more cars and have more houses and all sorts of things. But don't you also tend to have access to good medical care, access to prescription drugs, better food? You live in better houses, right? You're in houses that are heated in winter. Hopefully most of you are anyway, right? All those things that come with being wealthy, don't they also tend to encourage longer lives? Right? We get fed enough. In fact, probably we get fed too much. But if you go and look at those countries, then they have lots of TVs as well. Now, if you take the other extreme, if a country on average can only have less than one TV. That means half the houses don't even have a TV, right? You can imagine a country that was that poor that half the households didn't even have a television. Won't they also probably be countries where they don't have a lot of doctors or hospitals or medical care or good food or clean water and sanitation and all the other things that go with being wealthy? And doesn't that tend to negatively affect how long you're going to live? So that's an example of correlation. Nice straight line does not mean that this causes that. What you're seeing is in fact a lurking variable. In this case, I would choose that one probably. When you come to do some of the questions and they're in the homework and they say the same thing, you're given a box where you type in what you think the lurking variable is. And when you do that, there are lots of right answers. So don't worry too much about, is my answer the best answer that could be? Just find a reasonable reason for why this isn't causing that. But this is connected to that. Would you agree that average households are connected to being wealthy? So you could put along here the average income of a country and it would look very similar data. Are we good? Are we happy with what we just said? I'll take a thumbs up. That'll make me happy. Hey, thank you. We're good. So what I'm going to look at now is some of the homework. Thank you, Jim Tai. Let's have a look at screen 2. Now, what we're looking at here is our first homework question. I think I've made that maybe just a little bit too big. When drawing a scatter diagram, along which axis is the explanatory variable and along which axis is the response variable? If you remember, that was the first question I gave today. So let me just phrase it slightly differently. What's the x-axis called? Really? What's the x-axis called?
Horizontal axis.
Okay, thank you, Logan. So the x-axis horizontal and the other one vertical. This question is if something is positively correlated, right? That means its R value is a positive number. As the x increases, doesn't the y increase? So that will become as the response variable increases, so does the, sorry, I'll phrase that again. As the response variable increases, so does the explanatory one. I would phrase it the other way around, but I didn't have a choice. This is the same idea negatively. Here is a choice. Suppose the correlation coefficient R was near to being -1, right? So it was dead close to being -1. Which one of those would we describe it by? Well, I describe it as strong, right? But wouldn't I also, because it's near to -1, I would describe it as strong negative linear. And if it was near to +1, it would be strong linear and positive. And if it was almost 0, which of those 5 dots would you pick?
The third one.
Agreed. So you can see this, at least the beginning of this homework, isn't it going to be pretty quick, right? Just remembering what you do. Now, here we have 2 sets of them. I'm just going to do a bit of one, a bit of the other. Here are some scatter plots with no particular scales on them. That's nice because it makes it harder for you to judge things. So it's really just basically the sausage. Well, these two have good sausages. Would you agree this one isn't even linear? Agreed? Now, if the data is not linear, so B is not linear, you'll say no. Because this question is asking us linear correlation. It's saying, how close are these to being straight lines? And the answer is that one isn't even vaguely close to being a straight line. Would you agree that's, it's curved for water, better word. Okay, moving on then. Let's pick one. What do you think C is? Here are the choices for C. High, moderate or low, or none. What do you think?
High.
That would be great. Let's pick, I don't know. Let's pick B. No, moderate, or high.
High.
I would go high. Would you agree the sausage is quite skinny? Right. Would you agree this one would be more likely to be moderate? You see how kind of fat that sausage is compared to this one? Now, here we're going to do some of those lurking variable stories. So over the past few years, there has been a strong positive correlation, right? A nice straight line, positive meaning uphill, between the annual consumption of diet sodas, right? Diet Coke, right? And the number of traffic accidents. How on earth could that be the cause? Because I don't think it is. Now you could say, well, people drink Coke when they're driving like they do, you know, telephones and all sorts of distractions, but I'm not really convinced that's the real reason. So we have to find a different reason. So what could be the reason? And it's not because we buy a lot of Coca-Cola. What could be a reason for the increase in the number of traffic accidents over the last few years? Exclude this year, which is a weird year. I didn't quite hear that. I'm not sure if you were answering a question. So I will just put you on mute in case that's a private conversation we don't need to hear. So back to my question. What could be causing the number of traffic accidents if it's not how much Coca-Cola we drink? Got you stumped? I can't say I've got a good answer. I have an answer, but I'm not sure it's a good one. Before I go for it, anybody want to tell me theirs?
Would it be a variable of if they're drinking while driving, like drinking the soda while driving?
I wouldn't use that one. And I, for some reason of shouting that use, I would say it's an increase in population. Would you agree, even over a few years, aren't there more Americans than there were 10 years ago? And I'm assuming more Americans are more cars on the road, and more cars on the road mean more accidents. And aren't more people means more people drinking soda. So I'm just saying the population has increased, and when populations increase, don't lots of things associated with what they do just increase? Right, and that would be mine. I'm not saying it's a good one. You can come up with a better one that's even better. Over the past 10 years then, a nice strong positive correlation between teacher salaries and the cost of drugs, prescription drugs. I don't think the fact that I get paid more over the last 10 years is the main reason that prescription drugs have increased. They are definitely connected, but my salary does not directly affect the cost of drugs. So what might be the lurking variable?
That people can just afford.
Oh, so we're richer, and if you're richer, you can
Yeah.
you'll pay more for stuff.
Uh-huh.
Yeah, I would take that as a good answer. Any others? Because there's no right answer to this. There's like 10 right answers. I'm making that number up, but there's a lot of right answers, and that one's fine.
Teachers are on drugs.
Don't like that one. No, and I'm not.
Couldn't resist.
Yeah, you had to get it in. Okay, here's mine. Over the last 10 years, inflation. Do you know inflation just means prices of everything tends to go up through time, doesn't it? I mean, 10 years ago, wouldn't a house cost a lot less to buy than today? 10 years ago, wouldn't a car cost less? Now, there might be better cars today, that's true, but they're also more expensive. Doesn't everything go up in price? Doesn't your electricity go up in price? Doesn't your salaries hopefully go up in price? Which is what happened to the teachers. Inflation, that would be a single word description. Okay, do you think that the increase in average annual income, in other words, we are getting richer over the last 50 years in general, we are richer. We make more money, we buy more stuff because of that. Why should that affect the time to run the 1 mile? Because I don't think it does. So we're looking for quite a weird one, I think. And I'm not saying that my answer is any good, but I'd like to hear, if I could, what has happened in the last 50 years that has managed to make the time to run the mile go down? It used to be 4 minutes to do a mile, right? That used to be the number. But every Olympics since then, hasn't it go down, almost going down every 3-4 years? A few seconds here, a second there over that time period. What in hell, what is going on? What on earth is going on? There's the beginning of what I want. It's my answer, not the only answer. During that 50-year period, we've increased our knowledge on, what do you think? What have we increased our knowledge about or on?
Like going to the gym instead of going on a 1 mile run or something.
Yeah, yeah. When you look at how people used to train 50 years ago, wasn't the training pretty basic? You just ran the mile lots of times and maybe done some weight training. Today, don't, if you know anything about sports, talk to our professor if you get a chance. He'll give you lots of information. Do you know that high achieving athletes have got a lot of background to it? Some of them watch their diet. You eat certain things Don't you train regimens in totally different ways? Don't you have new machines to build the leg muscles and increase the oxygen level? We have just scientifically took over that process to get like the ultimate out of your body. You know, protein drinks. I'm just going right on here, but if you're into training, don't you realize that it's not just a matter of lifting weights? Isn't there a technique to do it? Isn't there good things to eat and bad things to eat, like protein or carbs, whatever it is? And before a race, they do certain things to get their body ready and so on. So I'm just going to say we've increased our knowledge of running. And that's very vague, but I've just described some of the things I mean there. Do you know, for instance, if you are in the American Football League, do you know that one of the people who gets paid for the Seahawks and all the others, they have their own dietitian? He will look at each person and the position that they play, because certain players need different things. Don't the big heavy guys need bulk? But don't the, you know, the quarterbacks don't want bulk? Don't the quarterbacks need flexibility and speed? So can you see that they would have different training things to do, different practices that would do, even different food that they would eat? And that's now quite scientific. And that would be my explanation of that. So you got some more. And now we get to a guy that, if I can remember last time, was quite an awkward thing to do. Remember trying to draw straight lines and things on this diagram? We're going to do a scatter plot. So here is the data. If you're interested, X is the age of the pony, and Y is the weight. Okay, so 360, hit the dot, go 360, 695, 695, 12,140. 15,156. And lastly, 24,189. Now, you might think they are good. I know they're not. These are kind of at starting positions. Now, I'll go to point 1, which is this one, and I'll click on it. And it should have been 3,60. So all I do is I tweak it. Because see, if you don't tweak it, WebAssign's going to say you're wrong. Now, point 2 was 695. So click on that, fix it. The third point was 12,140. The next point is 15,156. I'm actually pretty good when I look at it. It was maybe a couple out, but not much. 24,189. And we're done. There is our scatter plot. So far, so good. Now, would you say that this is low, moderate, or strong? Now, there's not a lot of data points, so, but can you imagine my sausage? What do you think that is? A fat sausage, a medium-sized sausage, or a skinny sausage? Because that's going to be the answer. What's your guesstimate? Well, I'm going to guess for us then. I'm going to say it's pretty strong. So what would it look like if it was moderate? Well, can you imagine I had more data points a bit like this? Maybe a couple more, make it a bit far. And what would it look like if it was weak? You can see it's even worse. That's what it would look like. Now, I'm going to have to kill off all these dots. And I should have planned this ahead before I did this. So you're going to bear with me because I need the original data set to continue. I wonder if there's a delete all. That would be nice.
At the top, it says clear all.
Okay. Oh, wait a minute. If I clear all, I'm going to have to plot them all, aren't I? What's quicker? Clear all. Only this time, I am not going to fix the data. I'm just going to do my best guesstimate and pretend I'm right. So I got that guy, 695. Can you pretend that that was in the right place? 12,140. 15, 156, and 24, 189. So would you say that this is positive or negative? I hope that's a pretty obvious answer. I won't insult your intelligence. I will say positive. You agree? Uphill. Now, we are going to compute R, the correlation coefficient. They have a whole load of stuff here that you don't need. And the reason you don't need it is because SALT does it for us. So what I'm going to do is I'm going to hit the SALT button. We're going to show you how you can use it to get the correlation coefficient. And the guy that you hit is regression. And it will say select variable, and you do X is the age and Y is the weight. And there's basically my data set, slightly different axes, but that's fine. There's my straight line, that if you wanted it. And the guy that's called the correlation coefficient is just called correlation here. And it's this guy, 0.9721. So 0.9721. That is very close to being 1, isn't it? Does it not kind of emphasize that my strong was a good answer? Suppose this number, this correlation coefficient, was 0.72. Then I would have moved this answer to moderate. Suppose it was 0.5. Then I would have moved my answer to low. So you've got moderate in this case, strong and low, and I'm picking strong. So if you held back until you answered this, it would probably make this one a bit clearer. And it's quite hard visually with there are only a few dots to tell how good a fit the data truly is. Now they go on and they say, as X increases from 3 to 24 months, does the value of R imply that Y tends to increase or decrease? Well, looking at that value of R, which is positive, we can draw the conclusion that Y will increase as X increases, right? They both go uphill. Are we good? Any questions about how we went through that? Okay, I will move on then. Here's another example. Here's another one. For speed, I'm not going to do the correct version, but here the number of employees, which is X, and the average administration cost, whatever that is. So if you're in business, I guess you know what that is. 3 out of 40 is here. Oops, hit the dot. It's about here. Then the next number is 735, which is about there or lower. Can I move that a little bit? There we go. 1530. 3627. If you hover over that point, I don't know if you can see it, but in very faint, can you see it says 3627? So I can actually tell that's a good one. Last one is 7420. So 74 is about here. 20 is about here. Right, that's what this data looks like. Okay. Here are some choices. Is it strong and negative, low negative, moderate negative, moderate positive, low and positive, strong positive? Well, I'm definitely not going to pick the last three. Would you agree this is going downhill, so it's negative? So is it strong, low, or moderate? What do you think?
Moderate.
I'll go for moderate. Now, I may change my mind once I find R. Let's suppose I do it and R is 0.92. Won't I change it to strong then? Let's suppose I do it and R ends up being 0.54. Then won't I change it to low? So we may go back to this, but I would have picked moderate as well. Now we're going to get the R value. Use salt. Go to regression. X is this fella. Y is this fella. And the R value is actually, would you agree that's pretty close to -1, isn't it? And that means that I'm going to change my answer. The R value is that number, which means that it's quite kind of strong. And if you're doing a copy and paste like I just did there, well, you make sure to rub out any false blanks, otherwise WebAssign might not introduce it. As this thing is getting done, do you see there's a straight line-ish? Right, how am I going to explain this? Do you know that the brain tends to look for patterns? And when I look at this data, my brain is making me see a curve. Can you see a curve now that I've said it?
Yeah.
Yeah. If you change the scales, in other words, you move the X scale different and you choose a different Y scale. If you change the scales, you can make things look different. You can make them look like they are a better fit. You can make them look like they are a worse fit. And it's only by a change of scale and perspective. Right now, my brain is seeing a curve because that's what my brain is trying to see. Your brain is kind of designed, it's hardwired to see patterns. Oh, and I got some answers earlier and I wish I had paid attention. Thanks, Derek, for your contribution to the answer about lurking variables. So back to this one. Let me show you in a kind of very crude way what I'm getting at. Okay, imagine that we got a set of data and it looked like this. Right? Which kind of looks like a moderate kind of data set, right? If I kept the scale on the x-axis the same but I doubled what the y-axis was. So instead of going 5, 10, 15, 20, I went, 10, 20, 30, 40, 50. Do you know that same data set would now look like this? Well, I'll have to put a lot more dots in for that to be true. Can you see that the sausage now looks much skinnier? And that's only because I went up, in a big scale instead of going up in a smaller scale. What that has the effect is, can you imagine that if you make the scale bigger or smaller, won't you stretch the sausage or crush the sausage? And if you take the X and make it bigger or smaller, do you see that in itself? That tells us that we have to be very careful about looking at a picture and deciding what strong, moderate, maybe even weak looks like. There is nothing in the world you can do to make a none really look much better. See if the data is a big blob of nothingness. Changing the X scale, changing the Y scale, it just looks like a different blob of nothingness. But if there is any kind of linearity to it, changing the scale can alter it. Which tells us, be careful about using pictures. Use the R value. So 0.9 is good. That's strong. 0.7 is moderate. 0.5 is, well, they're calling it low. I'm calling it weak. Right? And anything under 0.5 is pretty much not worth talking about. Right? There's no correlation, essentially. Are we a little bit more comfortable about how to use this thing to do your scatter plots? Because you can't actually do it on paper and then show them. That's kind of not how WebAssign works. And this bit here, use your calculator. Don't need it anymore because we did it on Salt. I guess I should pick another one, shouldn't I? Yeah, this one's as good as any. Do larger universities tend to have more property crime? University crime statistics are affected by a variety of factors. The surrounding community. So if you've got a university and it's in a seedier part of town, then you may well find crime increases. If you've got a university and it's in a really expensive part of town, because that university is 300 years old and the town grew up around it, then you're probably going to have less crime. That's just the way the world is. The surrounding community. Next reason, accessibility given to outside visitors. If you live in a university where you just walk around in the campus and you can't really tell if you're in the university or you're in the town, right? They almost merge. Well, in a situation like that, there's lots of opportunities for people who steal stuff to get in. But see if you're in a closed campus, almost like a gated community, where there's, security people around and they check to say that you're really a student and that you should be there. Can you imagine that would be a reduction in the crime rate? So they've got all these different things, and here are 8 universities in California. And here are the numbers that I'm now going to try very badly to plot roughly. 14.3 had 23 crimes per 1,000. Oops. So 14.3, 23. Say it's that. 28 and a bit, 68. 28, about 68. 24 and 39. Drag it down a little bit. 14 and 23. Well, those are almost on top of each other. 7.5 and 15. 27 and 30. Almost done. 16 and 15.
Are you supposed to be on the computer screen?
I am. Now that you've told me that, all you heard is me saying it. Oh, now you can see me doing it. There we go. And the last one is
Thank
20
you.
and 25. Thank you for telling me. 20 and 25. So, boom. Right, roughly. Yeah. Now, if I wanted to fix them, wouldn't I go over here and I'd change that to 14.3 and I'd make the next number 23. And you will have to do that if you want WebAssign to give you the points, right? But I'm not going to fix the others. It would take me forever in a day. So looking at this data, we're just going to go straight into R now. You notice that I haven't even bothered asking if it's strong and weak anymore. So hit this. Hit regression. And the variables are number of students, how many robberies there are. That doesn't look particularly straight to me. I mean, it's quite ziggy-zaggy. And how about our first correlation that's just moderate? You see it's a 0.7 something? But it's positive. So as X gets bigger, so does Y. So that's that one. So if you ever hear medical terms or business terms, and they say there's a strong correlation between this and that. Now, they may stick in the word positive or negative. They don't often do that, but I guess they should. So if I went and said to you, there is a strong positive correlation between your body mass index and your blood pressure. What I'm saying there is that the bigger your body mass index is, the more likely you are to have a higher blood pressure. So do you see what we're doing when we compare two variables like this? Is we're trying to see if there's any connection between them. And if it's a strong positive or strong negative correlation, then we know that these two things are very strongly interconnected. And it may not be that the first thing causes the second thing, but at least it gives you some insight to what you might look for as a measurement for it. So if I go to the doctor and she says, your BMI is far too high, I'm going to have to watch your blood pressure because that tends to go along with high BMI. Or you might find that there is a strong correlation between alcohol drinking and liver cancer. Probably because drinking too much alcohol does cause liver cancer. But regardless of that, couldn't they then say, well, that is an indication that these two things are connected. Sometimes they're connected because I'm causing it, and other times it's less obvious. Maybe BMI is not the reason you have high blood pressure. Maybe BMI, you're overweight, and overweight people don't exercise, they're couch potatoes. And maybe people who don't exercise and eat too much fat and are couch potatoes tend to have high blood pressure. Maybe exercise is the reason. If you don't exercise, you have high blood pressure. But at least it's a way of comparing them. The number of times I've heard politicians saying, this is proof that whatever it is causing this. Right. So they may say things like, poverty causes increasing crime. The more poor an area is, the more crime. And you could probably collect data on what the average income of certain areas is and compare it against the number of crimes that are caused in that same area. And I think you would find that poor areas tend to have much more crime than wealthier areas, right? So that may be a true connection, but it doesn't mean that poverty necessarily causes crime. Because there is another factor that they've also found out, and that is, do you know the biggest indicator of crime? I don't know if you know this, but you want to have a guess what's the biggest indicator of crime? Age. If you live in an area where there's a large number of 15 to 35-year-olds, there will typically be a lot more crime than if you live in an older party town, right? A party town where the average age is 50 to 70. You know, there's a lot of 50 to 70-year-olds. Why do you think that is the case? Because both areas could be equally poor. Why does an area with a lot of young people have more crime than an area with a lot of older people?
They have more responsibilities.
Yeah, younger people tend to be irresponsible. Not everybody. God, there's some really irresponsible old people and some very responsible young people. But in general, don't younger people tend to commit more crimes? They just do. There are not that many 70-year-olds who burgle houses or steal cars or mug people, right? There just isn't. There's a lot of 70-year-olds that do that. The vast majority of 70-year-olds don't do that. But a lot more 17-year-olds than 70-year-olds do it. And that's an age factor. As you get older, you get more sensible and you stop doing, well, I've never done it, but a lot of them stop doing it as well.